Hi there. Would you believe it? What you see on the bench is one of the earliest personal computers ever offered to the public. It's the Compukit2 from a UK company called Limrose Electronics, first released in 1971. Okay, between us, it's just a patch board for playing with TTL chips, but I suppose it allows playing with digital logic functions, and a bunch of patch leads that came with the Compukit2 are used to connect the chips into complete circuits. The claim of being one of the earliest personal computers comes from the site Early Computers. When the Compukit2 first came out 55 years ago, it used a tasteful wooden enclosure, but it had the same PCB as my box. I could not find anything on the web for this except the Early Computers entry, which also links to the specs you see here. Pause if you want to study the details. Let's have a look what lurks underneath the board. Mine is obviously a slightly later edition using aluminum profiles instead of wood panels. The PCB says copyright 1972. With the panel removed, you may be able to see that the space below the PCB contains only two D-cell battery holders. Okay, that makes sense. 4 times 1.5 volts is 6 volts and would work in running the power-hungry TTL circuits at least for a bit. Although there isn't any mystery left, I decided to open the thing completely to get to the PCB underside, for a reason you will see in a moment. I considered whether to remove the battery holder, but leaving it does not hurt and I can easily power it from my bench power supply. After the other side panel is removed, the PCB is free enough to slide out, and the whole enclosure collapses into individual sheets. The solder side is now accessible. Earlier, while idly playing with the switches, I discovered that one is bad, but which one was it? Ah yes, the one after the white push button. Maybe it has been used most often. It is sometimes blocking and at other times excessively loose. I decided to replace it while I have access to the solder side. From the underside, the switch in question is the one just below the red one. Freeing it isn't going to be very easy as the central wire is continuous, going through all switches. And talking about soldering, they certainly did not bother cleaning the flux residue. Should I clean it now? But it has done no harm for many years, so I decided to leave the flux alone and concentrate on the switch. I removed some of the solder using a solder sucker, but it's still not easy. I could of course cut the wire, but I decided to just desolder it from the neighboring switches first, which should give it enough play to disconnect from the bad switch. The wire to the plug board pin and the 1K pull-up resistor are kind of twisted around the switch contact, but eventually I get them off. And now the switch is free. All that's needed is to loosen the retaining nut. Take the bad switch out. Replace it with a similar switch, not a new one, but still working. And tighten the nut again. And of course connect it up, just like it was before, including the wires at the neighboring switches I disconnected earlier. Reassembly of the box needs at least 3 hands, and of course remembering which slots in the profiles were used. But it's all pretty straightforward. Was it worth the effort? Let's power it up. Just by itself, with nothing plugged in, the board draws 9 milliamps, which I assume is the clock generator. With 2 jumper leads, I connect the push button labeled S1 to one of the LEDs. I need 2 because the jumper wires are not long enough to do it directly. The LED lights up, so by default S1 has a 1 logic level. While pressing the button, the S1 connector is pulled down and the LED goes out. Okay, that works. S2 is the switch I just replaced. It does the same except that I don't need to keep it pushed, of course. The other switches S3 to S6 do the same thing. All this is working fine. So far I've only tried LED L1. How about the other LEDs? leaving S6 to produce a high level, and touching the wire to each other LED in turn shows they all working fine. The clock generator is next. Connecting a LED to one of its pins causes it to blink. Nice. What are the other row of 3 pins doing? To find out, I wire up a second connection to another LED and it blinks too, but with 180 degrees phase shift. That makes sense because by the looks of it, what we have here is a normal 2-transistor astable multivibrator with 2 further transistors as output drivers on each side. Lastly, testing the white switch at the clock generator. So far it was in the S position, presumably standing for slow. Moving it to the F or fast position and both LEDs seem to light. Of course they don't. The signal changes just too fast for the human eye. Incidentally, all that switch does is to connect the 2 larger yellow caps in parallel with the 2 smaller caps when slow is selected. Using 2 identical caps and a double pole double throw switch, the multivibrator duty cycle remains 50% in either mode. In slow mode, the clock frequency is about 0.7 Hz. In other words, it changes every 1.4 seconds. In fast mode, it runs at nearly 15 kHz. I remember that the original specs said something about 0.5 Hz and 10 kHz. Probably my board uses different components, or some caps or resistors have aged, but I'm not too bothered by that change. I just want to show one more thing. I mentioned that by itself the unused PCB draws 9 mA, but that's only true with the switches in the 1 position. If I put them into the 0 position, the current draw increases quite dramatically. This is because in the 0 position, the 1K pull-up resistor on each switch is connected to ground. Yeah, they were not too concerned about power consumption when putting this together. The unsteadiness of the current readout is because the clock generator is in the slow position, so its 1K pull-ups in the driver stages are quite noticeable too. Finally, one must take care never to accidentally connect a switch to the 5V rail, because setting it to 0 causes a short circuit. In this case, almost 100 mA, which is what I used as current limit in the power supply. After all this, I wanted to demo at least some actual circuit on this thing. A simple 4-bit binary counter in form of an 74LS93, for example. As you can see from the datasheet, it's actually a 1-bit flip-flop driven by clock A with output QA and a separate 3-bit chain of flip-flops with its own input clock B and outputs QB, QC and QD. To get 4 bits, you have to make a chain of 4 flip-flops. In other words, externally connect QA to clock B. Finally, we also need to worry about the 2 reset pins, R01 and R02. At least one of them must be low before anything happens. I start by putting the IC into the top right socket. It's only 14 pins, so the bottom 2 remain free. Next, a VCC connection to pin 5 and a ground to the opposite side. Connect output QA to clock B input as explained before. I put a wire in to connect both reset pins together and connect the combined reset to S3. Another wire to connect clock A to the clock generator. I also connect the clock generator to the first LED, L1, and output QA to LED L2, and output QB to LED L3, QC to LED L4, QD to LED L5. This should be it. A quick visual compare with the datasheet. Hold it, I made a mistake. Fixing it now. Clock B is actually 1 pin higher, and the same error for the 2 reset pins. And because of that, the wire to S3 has to move as well. But now it should be okay, hopefully. Let's power it up. With S3 set to high, all that happens is that the clock LED blinks because the chip is held in the reset state. Putting S3 to low, and now this amazing circuit starts counting in binary. Vintage computing in action. I'll let you admire it for a bit. Switching the clock to fast mode, and all we get is 5 LEDs lighting seemingly steady. Although the counter is effectively dividing by 16, the slowest LED, number 5, is still blinking about 1000 times per second, way too fast to see. If you want to count faster than with a slow clock, but actually see the LEDs blinking, I have to feed an external clock from a function generator. At 100 Hz, we can just see LED 5 blinking, but slowing the external clock down to 5 Hz gives a pleasing display of activity. Initially I wanted to expand this circuit with a 7-segment decoder and a display, but it turns out I have neither in stock. So the only enhancement I can offer is to expand the circuit with a pre-stage 74LS93, so we are having 8 bits instead of 4, but using a 74LS138 to decode the lowest 3 bits into decimal, or rather octal. To make the decoder do anything, the enable pin G1 has to be high and G2A and G2B have to be both low. Also, unfortunately, the decoder default output is high, so instead of a shining LED moving through 8 positions, we will see a dark LED moving through illuminated LEDs instead. Here is the finished circuit running again from an external clock. With the internal clock on slow, it would take a boring 22 seconds for LED L1 to change state, and at fast mode, the darkness would move through the LEDs at nearly 60 Hz, still way too fast to see. Well, I hope you have enjoyed this excursion into rather old technology, although one should be able to use this board with CMOS chips as well. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.